This is a topic which I've had an interest in for many years, and I think it's about to become very timely again, because there are, as you may know, there are several trials that are underway that will collectively randomize about 80,000 patients to receive either saline or some other concoction of fluids that we frequently refer to as balanced, because their electrolyte composition is closer to blood plasma. And the reason we think that's important has to do, at least in large part, although not exclusively, with its effect on acid-base balance. And it's been, I think it's easy to say that for many years, people have debated and not necessarily settled the issue of why giving saline causes metabolic acidosis, how does sodium bicarbonate actually work. And there are some, I think, more sophisticated ways to look at acid-base which shed some light on that topic. So the title I was given was, How Do I Analyze Acid-Base Abnormalities? Do I use Henderson-Hasselbalch base excess or Stewart? My disclosures are there. I don't actually think I'll talk about anything related to these products. I do have this disclosure, I suppose. Not enough people have bought this book, so I guess it's not really a financial conflict of interest, but it's probably an intellectual one at least. So let's begin with thinking about what we think the traditional acid-base analysis looks like, and that's largely dependent on where in the world you come from, and whether you essentially have learned acid-base through sort of a Boston tradition, which is based largely on what we call the 6 rules of thumb, or you come more from a Copenhagen tradition in which you've thought about or learned about using base excess as a way of getting at this. But neither of those by themselves is adequate to really understand acid-base physiology, particularly in critically ill patients. In normal mammals, many of these approaches are sufficient, but certainly in understanding critically ill patients. And over years, we've invoked other important mechanisms as part of that. We've talked about, well, there's abnormalities in renal tubular function, there's bone buffering, of course there's a Gibbs-Donnan equilibrium that gets disrupted in critical illness, and what effect does that have? And we've even had these constructs around things like formed bicarbonate. And if we put all that together, we have a very simple equation which you can remember, maybe write down, maybe put into your smartphone. And this is actually the traditional method, if you will, to understand something that as an intensivist I care about, which is I want to understand if I give a certain volume of a certain fluid, of a certain composition, what will happen to my patient? In other words, if I infuse a liter of normal saline, 0.9% saline, into my patient, what will their acid-base and electrolyte composition be? And of course, we have fairly sophisticated ways, although they're not perfect either, of understanding what will happen to the sodium concentration and things like that. But we don't really have anything useful to understand what the pH in the blood will be at the end of the day. And if you turn that around and you say, okay, now wonder if I dialyze against a dialysate of a specific composition, what will happen? Or if I use replacement fluid and I remove plasma water, what will happen? I want to know that as a intensivist. That's important to me. And yet I don't have good tools to understand that. So when the physical-chemical approach was introduced by Peter Stewart some years ago, more than a quarter of a century ago, in fact, and based on concepts that had been kicking around for more than a century and a half, it appealed to many of us because it was sort of another way of thinking about acid-base. And it's based on this idea that there are 3 independent determinants of acid-base balance. PCO2, which of course you're very familiar with regard to the Henderson-Hasselbalch equation. The buffers, which can be lumped together because they have similar pK, and something called the strong ion difference. And this particularly appeals to, I guess, the nerds of us, like me, who think that, well, look, if I already understand PCO2 because I'm measuring it, and I understand a little bit about how it works in terms of blood gas analysis, and I understand electrolyte composition a bit, and I can measure these things, and the weak acids kind of don't change very much. I have a model where I can really understand dynamic acid-base balance in a way that I can't really get to with bone buffering and considering, tubular physiology in ways that I can't measure. So this is appealing in large part because of its transparency. And I would argue it's actually not the hard way. It's actually much easier than dealing with all the things that I mentioned on the previous slide. Now, I realize putting all this together into a fourth-order polynomial equation could be a bit daunting, but none of us actually use that. Well, very few of us. I think Shelley Magner has this in his smartphone, and he probably pops it up and says, okay, I'll tell you what your strong ion difference is. But I think most of us use the concepts, not necessarily the numbers. For research purposes, though, of course, you can collect the data, and you can put it in a spreadsheet, and you can analyze it. And this model provides an ability to do that. So how do I analyze acid-base abnormalities? Well, I actually use all three. I mean, I think of this not as either or, but together. And the reason for that largely is that the components of the Stewart equation that I just showed you actually include both the Henderson equation, which if you apply the pH notation of Sorensen, you get the Henderson-Hasselbalch equation, and the bases, if you will, for base excess, the Van Slyke equations, which are shown for you there. And we know, we published this many years ago across a vascular bed where weak acids don't change and you can measure everything else. The strong ion difference and the base excess are tightly correlated, and in fact, what the strong ion difference is it is equivalent to the strong ion difference, or the standard base excess that corresponds to the change in the strong ion difference, or said the other way, the strong ion difference is the change in the base excess, which will correspond in vivo to a pH of 7.4 and a PCO2 of 40. Now, why is that? Well, the reason for that is that these concepts are simply measuring the same thing. So what the strong ion difference is it's the difference between the anions and the cations in plasma. This is the strong ion difference. And of course, it's filled by weak acids and the effect of PCO2, which is largely bicarbonate, and we call that the buffer base. And so the change in buffer base is the strong ion difference, or the buffer base is the strong ion difference. And the change in buffer base, of course, whether it goes up or down, we call that a base deficit or a base excess. So strong ion difference is just buffer base. That's all it is. It's what Singer and Hastings referred to as buffer base in the 1950s, and were the basis for the development of base excess. So all of these approaches are essentially the same, except in terms of their implementation. You can use Henderson-Hasselbalch equation to understand where a patient is on the map. You have a much harder time understanding why the patient's acid-base physiology is what it is, why their balance is what it is. Unless you look a little bit deeper, you can use semi-quantitative approaches like base excess. Or if you really want to look at everything transparently, you can use the physical-chemical approach. Is this necessary to manage patients at the bedside? Rarely. It's rarely necessary. Occasionally it is. Occasionally, and I'll show you some examples in a minute. But it's rarely necessary to understand what's happening at the bedside. It's useful as a tool particularly for research purposes. And it's the concepts, which I will try to reinforce in the next 20 minutes, are useful, in my judgment, at the bedside. But is it necessary to plug all these numbers into your smartphone and come up with an answer? I don't think so. I think you can get to the same place with base excess or Henderson-Hasselbalch. Okay, so I mentioned this equation. If you really want to understand the answer to the question I was posing, you can apply the more traditional acid-base analysis, but you really do need to approach it in a relatively complex way. There is no simple way of discerning what will happen to your patient's blood pH when you infuse an acid or a base or an electrolyte solution. And in order to get there, you not only have this complex equation, but you actually have some unknowns in this equation, which actually cannot be estimated accurately a priori. For example, this term formed bicarbonate is not something you can predict in a particular patient. So this approach becomes unusable in any way for research purposes or clinical purposes at the bedside. Conversely, this is some work that we did many years ago now, back in the last millennium, in which we showed that use of the Stewart equation can predict accurately what will happen if I infuse a couple liters of saline into a healthy dog by measuring what goes in and what comes out and simply plugging in the equations. Now, it's not perfect, but some of this was probably just related to lab error. So we predicted the pH to be about 728, and it ended up being about 726. And you can see that predicted and measured are somewhat different. Now, Trolls Ring and I, mostly Trolls, he's more of a nerd than I am, we looked at some data from Pittsburgh, and we wanted to see whether in the complex reality of giving all kinds of treatments to patients, changing their ventilator settings, giving them fluids, having them, none of these patients underwent CRRT, but drug infusions, various other things. Could you actually predict on a day-to-day basis what their blood gas would show based on this model? And you can see there's a lot of change on a daily basis related to all kinds of different things going on. And we picked, this is an example of a particularly unstable patient with wide swings, and yet the model, which is shown in red here, predicts very well what will happen to this patient. And in the aggregate, you wind up showing, this kind of correlation that where the model and the actual regression line are almost superimposed. There's two lines there, a blue and a red line, and in the back of the room, you can't even tell that they're different. So yes, you can actually predict what's going to happen to these patients. Do you care? Do you care? I see some people shaking their heads. They don't care. I see people nodding. Most people are just waiting to see what I'm going to say next. But do you care? Is this important to you, both at the bedside to know what's going to happen and conceptually to be able to understand what's going to happen? Well, I think it is, but let's walk through it and we'll see if we agree at the end. So this whole thing is sort of based on the concept of electrical neutrality. It's based on the idea that the body's not a battery. So if I change electrolyte composition in the body in ways that I can measure, like, for example, I change the chloride concentration by infusing large volumes of 0.9% saline, for example, I will alter this relationship. And so the first question I have for you is, according to physical chemistry and the physical chemical approach to acid base, how does saline cause an acidosis? And surely you must believe that it causes an acidosis, because there's ample evidence to support that now. Does it do so by decreasing the strong ion difference and therefore increasing water dissociation? Does it do so by diluting bicarbonate? Does it add protons, or does it distort the blood gas analyzer? And I'll ask you, if you have your application, to vote on that. And hopefully we'll have at least 4 people voting so we have some sense of the room's feeling about that. Excellent, excellent. So the majority of you chose the correct answer. Now, we could quibble a little bit about this increasing water dissociation. Water actually exists in a lattice. It doesn't really associate the way we think of it as H2O, and it doesn't really dissociate into protons and hydroxyl the way we kind of think it does in sort of, high school chemistry. But nevertheless, there is an effect of the strong ion difference on the pH. It's not because I dilute the bicarbonate. It's not because I add protons. This is very important, actually. I'm delighted that very few people chose that answer because this is something that's been kicking around in the literature, maybe not in the literature, but in the folklore in medicine for some time. People say, oh, the acid-base status is affected by the fact that normal saline has a pH of 6.5. Do you know why normal saline has a pH of 6.5? It's because its shelf life is longer if you add a tiny little bit of hydrochloric acid to prevent bacterial growth, and you can actually store it in your hospital for 20 years or something. That's not really true. In fact, the shelf life is actually not determined in the case of normal saline so much by bacterial growth, but rather by how long it takes for the plastic to break down. It's similar to your bottled water, although you have nice glass bottles here in this conference center. But that's the shelf life issue. But if you keep it at a pH closer to neutral, you do have a shorter shelf life because of and so it has no buffer in it. It's just salt and water. So you add a tiny little bit of hydrochloric acid, titrating down the pH, and that's why it's lower than 7. But it has nothing to do with its effect on the body, because if I took that tiny little bit of hydrochloric acid and put it in your saline and infuse it to you, your buffer system handles it, has no effect at all. The effect on, and in fact, you can do this experimentally. It's been done. I don't think I have a slide. Maybe I have a slide. I don't have a slide. But it's experimentally been done where people have taken various compositions of fluid and then titrated them to a specific pH and then infused them into animals. It has no effect at all. The effect is driven entirely in crystalloid solutions, driven entirely by the electrolyte composition and in fact, the strong ion difference. So how does that work? Well, here's a mythical 70-kilogram man. Sodium concentration, we'll say, is 140. Chloride concentration, we'll say, is 100 milliequivalents per liter. And to keep the math simple, because it's early in the morning and we haven't had but 1 cup of coffee, we'll just assume that the strong ion difference is the difference between sodium and chloride, and assume that all the other anions and cations just balance out, just to keep the math simple. And we now add 10 liters of 0.9% saline. We chose 10 liters because it's a large amount and because it's, again, 10, so it keeps the math simple. And what we find is that the sodium concentration increases, using the Adelman equation or whatever you like to sort that out. You're adding free water and sodium, and the sodium concentration goes from 140 to just about 143. But look what the chloride concentration does. It goes from 100 to 111. So there's a much larger effect on the chloride than on the sodium, and that results in a strong ion difference that is lower than you started. And I told you already that the change in strong ion difference is equivalent to the buffer base, and therefore the base excess or base deficit. So this is like having a base deficit of -8, driven purely by the saline infusion. Now, I've oversimplified this a little bit because you are also diluting the weak acids, and so there'll be a slight less of an acidifying effect because the dilution of weak acids is a slight alkalinizing effect. But nevertheless, there is an acidosis. And so what happens, if you will, is I change this balance. I can't change much to balance this out. What does change is the buffers, and that's why we call them buffers, because their concentration is either dissociated or associated with protons varies because it can. That's why they're weak, as opposed to the strong ions, which remain dissociated always. There's not much that can change over here, except hydrogen ion concentration doesn't change very much, but its effect, of course, is what we measure and what we care about, and that brings us back into electrical neutrality. You can map this out. This is a strong ion difference versus the pH or the hydrogen ion concentration. And you can see in part this is affected by the distortion that the pH scale produces on this relationship. As I decrease my strong ion difference, you and I have a strong ion difference of about 40. Our critically ill patients might have a strong ion difference closer to 30 because they lack the weak acids, albumin and phosphate, particularly albumin, to keep that in check so that that you wind up with a normal pH. So critically ill patients might start with 30 or 35. And you can see as I move in this direction, the pH falls and the hydrogen ion concentration increases. The hydrogen ion concentration increases much more rapidly than the pH, and that's simply because of the inverse logarithm that the pH scale imposes, and it makes the pH look flatter than the hydrogen ion concentration. Now, I mentioned that you could use various fluids and you could understand what was happening. This is actually a in vitro model, but it involves taking blood from humans. And in fact, this is John Morgan's group. And he took his own blood and the blood of his co-authors. So that's skin in the game. They didn't take too much blood. But they took it and they put it in a beaker and they diluted it with various fluids. And this is what they got, and what they found was that if you used a solution, an artificial solution, because we don't have one on the market like this, that has a strong ion difference of 40, no atote because it's just crystalloid, you could keep the strong ion difference completely stable in the blood. The base excess here would actually go up because you're getting a dilution of the weak acids, which is the other half of the equation that I mentioned. The slope of this line, though, is much flatter than the decrease that occurs when I dilute the strong ion difference to zero. And you can see I get this big drop and I get this big effect on base excess. So this is the experimental evidence to support the models that I showed you. So question 2 is, of the options listed below, which is the most accurate way to screen unmeasured ions? So we're going to move from the easy stuff, what happens when you dilute blood plasma with crystalloid, and we're going to talk about things that are harder to measure. These are unmeasured anions, and I'm going to show you how the various approaches to this acid-base physiology allow you to understand what's happening there. So, do we use the anion gap with a range of 12 to 16? Do we use the gap of the gap? Do we use the strong ion difference? Do we use an anion gap using this equation? This is international units down here. Or do we use the anion gap with a different normal range? Which approach do we take? And we'll start. There we go. Okay, well, we got a nice spread. We got a nice spread there. The correct answer is actually D, so the majority of you, or at least the plurality of you, voted for that. So you can't use the quote-unquote normal range, because I said it was in most critically ill patients, and most critically ill patients, you can't use the normal range because the anion gap is made up of things like albumin and phosphate. And particularly albumin tends to be low in your critically ill patients. So you can't use the normal range. It's not predictably low, such that you can just say, oh, I'll use a different range, because some patients have more or less albumin. Some patients have very, very low albumin. Some patients have normal albumin. The average patient has a lower than normal albumin. But you're not taking care of the average, but you don't go to work every day and say, okay, what's the average antibiotic to use today? You pick specifically, and you do that when you're trying to analyze an acid-base problem. You are specific to the patient's electrolyte composition. So you can't use any easy overall range for albumin or anion gap, because the albumin is not changed. So albumin is a weak acid. So as it changes, there will be a change in the expected anion gap, and the same thing will be true for phosphate. So the easy way to get at this is to go and see if I can go backwards. How about that? So the easy way, in my units, it's 2 times the albumin plus half phosphate. In international units, it's 0.2 times the albumin plus 1.5 times the phosphate. That's how you get there. And what does that give you? That gives you what the anion gap should be without any unmeasured anions in a particular patient. And I'll show you some examples of that in a minute. Why is this important? It's important because there can be missing anions in the blood plasma, and that can be extremely important under situations like poisoning and things like that, that you cannot afford to miss. Now, you can make it more sophisticated by measuring not the strong ion difference, but the strong ion gap, which I'll talk about in a moment. But here's the problem, right? So I start out with, this is a normal range, and I'm able to see a change in the anion gap because I add these other anions and the anion gap expands. This would be a normal person. The problem is this doesn't work very well in critically ill patients, and this has been shown in multiple studies where you have a normal anion gap and yet a high lactate concentration, for example. And the reason for that is that if I start out with a normal anion gap and I add lactate, I get a change. But what happens if I start out with a very abnormal, low anion gap because I have low albumin and maybe I have low phosphate as well? A very malnourished patient will always have a very low anion gap. Now I can hide a certain amount of unmeasured anion without any change, without any abnormality in the anion gap. The anion gap changes just as well, but you probably didn't know what the anion gap was when the patient was home before they got sick. And so simply looking at an anion gap doesn't allow you to understand what's happening. We can close that gap, as I said, by using the simple equation. This becomes inaccurate, just so you know. It becomes inaccurate when the pH is below 7, so 6.9, 6.95 pH. I don't see too many of those. It starts to unravel. And when you get up above about 7.6, it starts to unravel as well. But within the physiologic sort of, compatible with life kind of acid-base range, this equation works pretty well. Now, I did mention that you can use not strong ion difference necessarily, but a component of strong ion difference, what we call the strong ion gap. And what this is taking advantage of is that there's the strong ion difference that you can measure, and we call that the strong ion difference apparent, which is the electrolyte composition and the difference between the cations and the anions. But there's another way to estimate the strong ion difference, which we call the strong ion difference estimated, and that is by calculating buffer base, because this has to balance. So I can estimate the strong ion difference from the bicarbonate and the weak acid concentration. Those should balance out. And in fact, in most of us sitting in this room, the difference between those two ways of calculating strong ion difference is less than 4 milliequivalents. It's very tight. But in critically ill patients who can have or any patient who has an unmeasured anion or an unmeasured cation, although those are rare, you can have an abnormality in what we call the strong ion gap, the difference between the strong ion difference apparent and the strong ion difference effective. And this has been shown in some studies to predict outcomes. So this is in trauma patients who were resuscitated in the emergency department. These are patients who came in with motor vehicle accident, gunshot wounds in inner city Philadelphia. And Lou Kaplan and I analyzed these data some years ago and showed that strong ion gap was actually a predictor of mortality in a very strong way in this side. So I'll show you an example in a minute, but the conclusion really, I think, is that Stewart's approach is mathematically correct. I didn't have time to build all of that for you, but it's based on basic thermodynamic equilibrium equations, which have been around for about 200 years. Well, the equations have. The physics have been around for much longer, as you know. It's only equivalent Henderson-Hasselbalch in totality when the system is completely open and when weak acids are constant, meaning that it rarely is true in the ICU. It's actually pretty easy to learn and easy to teach. It's harder, I grant you, if you learned acid-base physiology the traditional way, but it's certainly not inaccessible. It adds another perspective, if nothing else, to the way one views acid-base physiology. And I invite you to take the Stewart Challenge. You can go to a variety of different online applications. This is ours. You can go to the website and you can download this spreadsheet. It's an Excel file. Or you can download the R script if you're familiar with using it from the PLOS One publication that I showed you. You can add patient data. This is the best way. I've been putting this challenge to people for about a quarter of a century, and no one has ever sent me a case that doesn't fit. So I should offer a cash prize if you can show me a case that doesn't fit. But see for yourself. I think that's the best way. So let me show you an example. I think I have time for an example real quick. So this is a particularly interesting case because this was a patient who, unlike most cases, we actually had some pre-illness, pre-morbid data on this patient because the patient had a visit to the emergency department about a month before, and she had a set of electrolytes and acid base. She had blood gases checked. And the reason she had her blood gases checked then is because she had this very low bicarbonate. She's kind of approaching end-stage renal disease, and she had a bit of renal tubular acidosis and renal failure. Someone said, oh, okay, I better measure a blood gas analysis. And her base excess was pretty low. But this is kind of where she lived, kind of pre-dialysis renal failure patient. But then she comes in shock, fever, chills, and she was resuscitated. The other reason I like this case is she was resuscitated with about 9.98 liters, I kid you not, of normal saline. So almost exactly 10 liters of normal saline. Because her blood pressure was low and she was in shock. And this is her numbers before, and this is after resuscitation. So how do we approach this? Well, you can approach it in a variety of different ways, right? And as I said, you can use Henderson-Hasselbalch, you can use base excess, you can use strong ion difference, and you get pretty much the same way. And the way I approach it is the first question I ask is obviously this is a metabolic acidosis, but is there, and I'm referring to this column right here, before resuscitation, is there a respiratory component? Is this just a pure metabolic acidosis, or is this a mixed acid-base disorder? And then you can get at that in a variety of ways. You can use Winter's formula, which is 1.5 times the bicarbonate plus 8. Or you can use the Slichtig formula, which I like a lot better because it's easier to remember. You just take 40 and you add the base excess. The base excess here is negative, it's a base deficit, so you would subtract it. So you take 40 minus 18 and you get 22. And again, this is sort of plus or minus 2, and you can see the PCO2 is exactly where it should be. So this is a pure metabolic acidosis. There's not a respiratory component. The next question is, well, what kind of a metabolic acid-base disorder is this? And the anion gap is shown for you here. And because we had a prior gap, you could assume that this is an acute change, and so there's an increase in the anion gap. You don't usually have this available, so you'd have to analyze this. But either way, you can see there's been a change. Now, you can ask the question, what should the anion gap be? And the way to get at that is to look at the albumin and phosphate concentration. And so it was 20 and 1.5. It's now 23 and 1.6. And you can use the formula to determine that back here, it should have been 6.3, and it was 10.5. What are the missing anions? Well, there are probably some organic acids, sulfate, and some other things in a chronic renal failure patient. And there's only 4 milliequivalents. And I didn't even tell you what lactate was because there wasn't measured back then. Let's say lactate was 1 milliequivalent. Now, what about now? It should be about the same. It was 6.3. It should have been 6.3 before. It should be 7 now because 0.2 times the albumin plus 1.5 times the phosphate gets you 7. But it's 20. So I've gone from 4 missing anions chronically to 13 missing anions. What do you suppose those anions are? What do you suppose they are? Yeah, they're lactate, probably, right? And that's what, the docs taking care of her said. Oh, it's lactate. Whoa! It's a lactate. 5 milliequivalents of lactate. Very abnormal lactate. So that's it. I'm done, right? No, because you can quantitate the change. It's not just about figuring out whether there's anything abnormal here. It's also figuring out whether the amount of abnormality, the degree of abnormality is appropriate. So I told you there were 13 unexpected anions here. I've only accounted for 5 of them. What's the other 8? What's the other 8? Could be anything, okay? In the right context, this could be if this patient was, found down in their garage with a history of chronic alcohol abuse, you'd be thinking about ethylene glycol and things like that. This patient's probably septic, so it's probably a variety of different acids that are known to increase in sepsis. If she had malaria, it turns out that the malaria parasite actually contributes to the strong ion gap, and that's been shown in a number of publications from Southeast Asia. But here it's probably sepsis. But nevertheless, I'd like to know the answer. So if I back out the lactate, I still have, from this 13, I still have 8 milliequivalents of unmeasured, and that's what I get if I use the strong ion gap. I get about 7.8, which is just about 8. Now, what happens after resuscitation? What happens after resuscitation? She got worse, so maybe she needs more saline. Right? Well, the lactate actually went down, so it's not because she's under-perfused, at least in terms of how I can measure perfusion by lactate, which of course is not particularly sensitive, but nevertheless, the change is right here. She had a big increase in her chloride concentration. That's the problem. We've created an iatrogenic hyperchloremic metabolic acidosis in a patient who can tolerate it very poorly because her starting strong ion difference was low. And we've given her 10 liters of abnormal saline, and we've added insult to injury, if you will. And that's why her acid-base abnormalities have gotten worse. And I showed you all of that before. So she's down here somewhere, and I gave her enough saline to drop her. That's what's happened. She's pretty close to the edge of the cliff at 7.04. This is a real case. It's a real case. Okay, so here we are, and I've got all of this happening, and it's clearly coming from the chloride. It's clearly resolving what else is happening. But look, her strong ion gap, her unmeasured anions are the same. They haven't changed. What are they? Again, this is in a septic patient, which we believe this patient to be. It's probably these other anions that I mentioned. But you need to find out. So you need to measure an osmolar gap. You need to look for potential other causes of an unexplained anion gap metabolic acidosis, because the lactate doesn't explain more than it's just a small fraction of the unmeasured ion gap. So putting this all together, strong ion difference is equivalent to buffer base. Therefore, the change in strong ion difference equals the base excess or base deficit, depending which direction it goes in. The anion gap is composed of weak acids plus lactate plus the strong ion gap, so it's kind of all those things together. The way to parse that out is to adjust for the A tote, the A minus at least, using this formula, and then in that case the anion gap corrected approximates the strong ion gap. The standard base excess will be determined by the unmeasured anion effect, the lactate effect, and then the chloride effect, if you will, or really the strong ion difference effect. So how much, and if you were paying attention, you'll get this question right. So this is a test of me to see how well I've conveyed this to you in the last few slides. How much will 1 millimole per of lactate, how much will it raise the anion gap? By 50%? By 1 milliequivalent? It cannot be determined. By half a milliequivalent, or it depends on whether it's L or D lactate. I'm going to ask you to vote on that, and then we'll conclude. Okay, I would have liked to have done a little bit better, but not bad. So yes, it's exactly 1 milliequivalent. That's because lactate has one charge. Okay, it's a monovalent cation, monovalent anion. Sorry, and so every 1 millimole change in lactate will cause a 1 milliequivalent change in the anion gap, all other things being equal, and therefore you can quantify the change. If the lactate is 5, then the anion gap should increase by 5 milliequivalents, all other things being equal. And in the example I showed you, that's why I kept saying they're unmeasured anions, because the lactate is elevated, and you can back out the lactate from the missing anions. We had 13 of them, 13 milliequivalents. We had 5 by lactate, so that left 8 that were unexplained. L or D lactate, by the way, they're still both monovalent anions, so it doesn't matter. Okay, thank you.
Thank you very much, John. Very nice presentation. We have still room for some discussion, for some questions. I have some questions here on the app. So maybe I start off with this one. What actually causes the acidosis in lactic acidosis, since it's not directly the lactates?
So many years ago, some cell biologists put forth a concept called unreversed ATP hydrolysis, and in vitro, they reasoned that if you metabolized lactate to pyruvate or pyruvate to lactate, you don't produce any additional hydrogen ion. Therefore, the hydrogen ions must be coming from somewhere else, and this concept of unreversed ATP hydrolysis came about. But the reality is that it doesn't matter. It doesn't matter where whether the lactate has a proton with it when it's formed or not, because it's a strong acid. Chemists will call it a weak acid because the pK is 3.5. But to us in biology and medicine, it's a very strong acid, because for every one molecule of lactate that is associated with a proton, the 3,000 of them are dissociated. So it's a very strong acid in our terms, okay? And if we add it to blood, it will cause, because it's it's just like adding chloride. It will cause an acidosis. You can think of it as a change in water dissociation. If you're a purist, you know that that's not exactly the case, but it will change the pH simply by adding. Now, if I add sodium lactate, that's a different story, because the salt of a strong ion is not a strong ion. That's like adding pure hydrochloric acid versus adding sodium chloride. I will still get an effect for the reasons that I talked about, because the chloride increases more than the sodium if I'm adding equal amounts. And if I add sodium lactate, I will add sodium and I'll add lactate. What happens, though, when I do that? Well, that's actually very interesting, because if you add sodium lactate to a patient, they actually develop an alkalosis, because the lactate gets metabolized and then the sodium is left to move the strong ion difference in the other direction. But not acutely. So back in 1987 or 88, there was a paper in high-volume hemofiltration using lactate-based replacement fluid. And in that case, you could give enough sodium lactate rapidly to actually develop first a metabolic acidosis and then a metabolic alkalosis. Why? Because giving equal amounts of sodium and lactate, sodium increases slightly, the lactate increases a lot, and you wind up with a strong ion difference shifts slightly downward, and then as the lactate's metabolized, it goes back the other way. So it's just basic acid-base chemistry. If you give the salt of a strong acid, it's not quite the same as giving the acid itself. But in fact, lactate will, as will pyruvate, cause a metabolic acidosis.
I see. Could you go to the microphone?
John Vasiliadis, I'm coming from Greece. I would like to ask you something. In the Stewart's book that you've already mentioned, it explains the low pH of the normal saline, that it's caused by the different pK of the hydrochloride and the sodium hydroxide. It's lower of the hydrochloride, and so it says that explains the low pH of the normal saline. But the acid-base literature, I've read something about getting carbon dioxide in the solution, and which is the right answer, if you know?
I'm not sure I got all this. You're asking about the pH
the pH of the normal saline,
okay,
which is low.
Yeah.
Stewart's book refers an explanation by the different pK between the sodium hydroxide and the hydrochloride.
Yeah.
The hydrochloride.
Yes. Okay, so if you're a purist, okay, if you actually take and you mix up in the laboratory and you take 154 milliequivalents of sodium and 154 milliequivalents of chloride, and you add them to a beaker of a liter of water, pure water, not tap water, by the way, but pure water, distilled water, and you will find that, and you use a sensitive pH electrode, you will find that it's not exactly 7.0. It's about 6.9, 6.95. It's slightly off, and the reason for that has to do with the activity of these electrolytes that are slightly different, okay? Chloride activity and sodium activity, but that's tiny, tiny, tiny little effect. What I was saying was that if you then say, I'm going to make in a manufacturing plant a solution for infusion and call that 0.9% saline, the standard practice, and if you read the package insert, you'll see that the solution has been buffered to a pH between about 6.4 and 6.7. And the average that I've measured is about 6.5. And the reason for that is not related to the sodium and chloride activity, but it's related to the fact that they titrate the saline bag with a tiny little bit of hydrochloric acid in order largely to extend the shelf life. So that's the reason. And fundamentally, it doesn't matter, because I could lower the pH in the solution to 4, and despite the fact that it would cause a phlebitis when I infused it, it would have no different effect on your acid-base physiology. because you have buffers in your blood. Yes, sir.
Thank you very much for a very nice talk. Things we should know, but always they go to the background. So I take it home again. But I was thinking, as by nature, many of us, like myself, are a bit lazy. Would it be meaningful to introduce this, for example, the strong iron gap into a patient data management system so that we get a watchdog telling us that here there's really something going on that is unexplained by what we see? Or do you think it will be too much wrong information?
Are you asking me whether it's important to precisely measure the missing anions with something like strong ion gap, or is a corrected anion gap sufficient?
And calculated into your automatized patient data management system so that it just pops up every morning with the other information?
Yeah. Yeah, so there are many places around the world where laboratory medicine experts have told me that in their hospital they don't report an uncorrected anion gap for exactly that reason. The problem in the United States is that you know, because we're very penny wise and pound foolish, we think we can control costs by moving things around at the margins. So we tell people, oh, don't measure albumin and phosphate routinely. You know, just measure it when you need it. So you'll get back an electrolyte panel, and it will have sodium and chloride, and somebody will calculate the anion gap without measuring or thinking about the albumin or the phosphate. And so if we tried to implement a standard approach where we corrected them all, we would have to measure albumin and phosphate, and people would think that that was not very cost effective. And in point of fact, for the average patient, it may not be. So the solution could be, don't report the anion gap in the electronic medical record unless you have all the information, and make people work through that so that they understand it. That might be a better approach. In terms of the comparison of anion gap corrected by the simple formula of albumin and phosphate versus strong ion gap, people have sent me over the years, people have sent me examples where the strong ion gap was elevated more than it should have been by the anion gap corrected. And usually it was because the pH was at some extreme. The patient's blood gas, you know, was 6.9, you know, pH, and the effect of albumin and phosphate. But there was one case someone sent me from somewhere in Eastern Europe, Lithuania, I think, and it was a rare familial albumin disorder where the albumin was not, conformationally was different, and it had been described in the context of drug binding. And it turned out that this albumin molecule probably had less histidine moieties, and it just didn't have the normal acid-base principles. So it was fascinating. I tried to get him to write it up. Maybe he did, but I've never seen it in print. But that was a good example of where there really was a difference, but, you know, 9 million to 1, it's not going to be any different.
I'm afraid we're already 5 minutes over time. I'm sure we can go on for another hour. Thank you very much. It was a great session to my feeling.